Aloha everybody. Today I have a really exciting presentation called Ocean Waves, and basically it's a summary I made about a book called Waves in Oceanic and Coastal Waters. This book is hands down my favorite book on ocean waves. It goes really deep into swell spectrum, swell generation, propagation, and ultimately how waves end up on shore. I made this mostly for the Downwind hydrofoil community. However, if you're not part of that community, that's awesome. Please enjoy. And I guess my last note is that there's a lot of information in this PowerPoint. Really, this could be like a whole semester in a college class. So follow along, but also, we're living in 2026. Might be good to open up a chat GPT tab, and every slide where you're not feeling completely certain or you still have questions, ask ChatGPT and do your research, make sure the links are verifiable and everything. But there's really just so much information that I'm not going to be able to cover in this 40 minutes to an hour. And I gotta say, ChatGPT's been pretty accurate and they can work through some good examples with you. So this is going to be a lot. It's going to be a little math heavy, but not too bad. And I'm going to even skip through a couple of the slides that are just kind of irrelevant to this presentation. So here we go. Okay, so a wave is simple harmonic motion, and math people like functions to describe harmonic motion. In the case of downwind foiling, we are talking about surface displacement. So that's basically given at some point in the ocean with respect to space and time, you're going to be at a height above the mean water line. Okay, so in this case, eta, which looks like an n, is going to represent our surface displacement. And the function, the equation that we're going to use to describe it is a for the amplitude times cosine of kx minus omega t. And most of us are probably familiar with the period, which is represented by t, and that's just the time for a wave to complete one cycle. Next, we have L, which is the wavelength, and this is the distance for a wave to complete one cycle. Amplitude, this is not wave height, it's half of wave height. So if you hear your buoy says 6 feet at 13 seconds or whatever, the wave height would be 6 feet and the amplitude would be 3 feet. Amplitude's from the mean water line to the crest of the wave. Next, we have wave number and frequency. If you're familiar with the idea of frequency as cycles per second, the wave number's analog is that, but with distance. So it's cycles per unit distance. Okay. Up top we have just this animation of the wave propagating from left to right. Here I'm just showing the amplitude, the length, and that should be enough to get us started. Slide 1. Next slide. So this is one of those slides we're going to skip really quickly. There's a lot of math behind it, but basically the takeaway is we can get particle velocities and pressure fluctuations through all this fun math up here. Okay, linear wave theory. So in math, linearity means that you can add things together and it'll still work. And in this case, we're going to be talking about a red wave and a blue wave, and they have different frequencies, so they're going to be traveling at different speeds. But here we see the red wave and the blue wave are 2 units up from the center, right? So when you add them together, you should expect a new wave to form at 4 units height. And really select any point along this line. Maybe, it's going to be tough to say, but somewhere around in here, the red has a height of 0, the blue has a height of 0. Well, I guess at this point more like 1. So when you add them together, it's going to be like half. And that's about where it is right there. So these red and blue waves add together to create a green wave. And what's fun is when time goes on, so let me go forward and then back, this green wave has a really irregular shape and beat to it. If you're a downwinder, you've probably recognized this before. If not, that's great too, because we're going to talk about it some more. So a note before we move on, in the ocean, there are an infinite number of waves we can add together. In this example, it's just 2, but in the ocean, it's infinite. So this green wave could be a lot more complex. Okay, next page, linear wave theory, dispersion. So basically what we learned in the last slide creates group velocity and phase velocity. If you're looking at this animation here, these green circles represent the group velocity, and this red square represents the phase velocity. And in common terms, as downwinders, the green circle is kind of the pack of waves you're traveling with. You're going to be, turning off generally and catching the one behind it, riding the pack of waves. And then this red square is kind of like the fast waves going through the wave pack. Sometimes they go so fast they pass right under you, or sometimes if you're racing, you're going to try to stay up really fast with one of these squares, so you can pass the wave group you're on and jump into the next wave group and therefore, make more ground. So covered that. These speeds can be derived from the dispersion relationship, and the dispersion relationship is really a relationship between wavelength and period. And if you're a dispersive wave, that means the propagation speed depends on wavelength. Okay, so in deep water, phase speed is going to equal twice the group speed, and in shallow water, phase speed is going to equal the group speed. So this example right here is deep water. We see this red phase speed moving, twice the green circle. But if you come to shallow water, the red and green will be moving about the same. So that's why waves, when they come to shore, imagine Waikiki, the set maintains its shape for the most part as it comes to shore. Each wave holds its position. There'll be a little bit more on the next slide about that too. Okay, so now let's talk actual speeds. So in speeds, we're going to talk about a distance divided by time. So c for the speed is equal to the wavelength divided by the period. And through some math here, the modified dispersion relationship, we will have 2 scenarios. So there will be a deep water scenario and a shallow water scenario. In the deep water scenario, the speed is equal to gravity times the period divided by 2 pi. And in the shallow water scenario, we have the speed equal to the square root of gravity times the depth of the ocean. When you do these calculations, gravity is in meters per squared seconds. So you're not going to get mph or any unit like that out of that. So just keep in mind when you're converting. Again, deep water phase speed equals twice the group speed. Shallow water phase speed equals group speed. Okay, now let's take a bird's eye view of waves in deep water, so open ocean. From above, we'll see crests traveling in all different directions. In this case right here, where my cursor is, we have short crested waves. They're not very wide, and they're pretty close together, so the period's also pretty short. Let's call that a wind swell traveling towards the northeast. Down here, we have long crested waves, more spaced out. Let's call that a ground swell heading towards the north. In the middle here, we have the waves being added together. This is the linear wave theory. And where the waves align, they will construct and create larger surface elevations, and where they don't, where they're misaligned, they will create destructive interference of the surface elevation. So you're going to kind of get, a crossed up see-through here. Don't forget, in deep water, short wavelengths travel slower than longer wavelengths. So this set of waves is going to be traveling faster than this set of waves. Now, instead of the deep water scenario, let's look at the bird's eye view of a shallow water scenario. There's 4 waves. A shallow water wave may change its direction or shape. If you're a surfer, you should be very familiar with shoaling. That's as in a wave comes towards the shoreline, it's going to slow down because of the depth, and as the depth, as the as the wave decreases in speed, it's going to get a more bunched up wavelength, and that's going to increase its amplitude. Next, we have refraction, which a lot of people confuse with reflection, but refraction has to do with the speed of the wave as it approaches shore. So if you think about your favorite surf wave and you've noticed it change direction, it's probably because one spot of the reef or sandbar is more shallow than the spot to its side. So it's turning towards the shallower section of the reef. The best analogy is, imagine pushing a cart, and on one side of the cart there's all sand, and on the other side of the cart there's all concrete. The cart is going to turn towards the sand because the wheels will rotate slower on the sand and faster on the concrete, turning the cart towards the slower section, which is the sand. Next is diffraction, which is, I'd say, the hardest to understand or visualize, but basically if there's a wave amplitude that's irregular along the crest being this right here, when there's an irregular amplitude along the crest, the wave will turn towards the area of low amplitude. The easiest way to see this is when a wave shoots past a seawall. So imagine a wave coming into like a harbor, and on the other side of the seawall, it's open ocean, so the wave continues. But there's also a leeward side of the harbor wall. And as that wave passes by, it's going to spread out towards the leeward side. Next, we have reflection, and these are your classic jetty wedges and stuff like that. So the wave will pile up on an object, and then it'll release off the object, and that'll create a new wave, and pretty much every single time with a new direction and shape. Particle paths. This is very important and pretty easy to understand. Very, very relevant to what we do with hydrofoils. So as you've probably noticed, there's a pattern of deep water and shallow water analysis. In deep water, which is defined as a wavelength, when a wavelength is less than twice the depth of the water, the orbit retains the shape of a circle with the amplitude as the radius of the circle. So here we have on the surface of the water, this represents the particle, and it's going in an orbit. And then as you go down, so according to this bullet right here, this orbit is going to decrease in size. So it's going to become really small like this. And at the very bottom, it's going to cease to exist. You won't notice it at all. Okay. In shallow water, it starts off about the same. So at the surface, it's close to a nice orbit, but the lower it goes, it turns into an ellipse. So instead of this circular motion, the lower you go, it turns more sideways like this. And once you get to the very bottom, it's just going to be all side-to-side motion. Keep in mind that the wave energy is propagating to the right in this case, but these little particles of water are just doing this orbital motion. And when we're writing our foils, we got to kind of differentiate the two. So you want to stick with the energy of this wave because that's what's going to get you somewhere fast. But using these particles, especially the vertical part of this motion, is going to push up on your foil and really help you get the lift and go fast the way you want to. And when the particle goes down, you will get less lift, so therefore you're going to have to find some energy some other way. Basically, you want to be on the up part of the wave right here. Next slide. Okay, so let's talk a little bit about buoys. This slide's called Processing the Signal. Buoys are the most common way to make wave observations, although there are a couple other methods, such as satellites and even wave observers as humans on a ship. Buoys are kind of the best. And buoys are going to use pitch, roll, yaw, heave, surge, and sway to determine sea state characteristics. Basically, they'll take vertical displacement as a function of time, and then you can integrate the acceleration measurements. You can get the surface displacement, so that's going to be your eta that we talked about earlier. The analyst, then determines the most useful way to process the data. So most of the time they're going to use a fast Fourier transform, and you can determine where significant contributions of energy can be found dependent on frequencies. That's a mouthful, but we're going to get into that more on the next slide. So basically all of that creates this, the variance density spectrum. So here we have our buoy, here's the time, and then that vertical displacement we were talking about, and this is our time series altogether. Via your fast Fourier transform or zero crossing algorithm, which we did not get into, you can create this plot. And here we have energy density, which has peculiar units if you're not used to them, meters squared per hertz, and this is versus frequency. The units, of course, they're important, but they're not too important to us as downwinders. It's really the shape of this spectrum, just visually. You can analyze a lot with it. This is only one dimension of the frequency spectrum. A two-dimension spectrum would also include direction. Okay, so the variance density spectrum continued. The book that I mentioned at the beginning of this presentation describes the variance density spectrum as the most important context in his whole entire book. There's too much to get into right now, but this is kind of the basis of all buoys and all of these plots right here. It all comes from right here. And what we can do with this, besides the visual analysis, is we can take some moments of the wave spectrum. So some important moments that you all are probably familiar with are significant wave height, even mean wave period. There's many more, but that's just a couple. And a fun note is that right here we have 4 times the square root of m naught has a significant wave height. And a lot of us as surfers were taught that the significant wave height is the average 1/3 of the tallest waves, which is kind of true, but this is really the theoretical significant wave height. Okay, let's do some examples of the variance density spectrum. So really, it's the width that's going to tell you the most about what the ocean's doing. So on this example, we're looking at a narrow spectrum. So right here at about 15 seconds, we have a really narrow spectrum. Really nice peak right there. And these are the waves we'd probably expect to see. Lots of waves lined up, equally spaced, long crested, very regular. While wide spectrum, as we can see from here, where we have about 10 to, 7, maybe even a little further, definitely into the 6 period. When the spectrum's wider like this, we'll have a lot more irregular waves. So waves traveling in different directions, differently spaced out. This picture is really a little too dramatic for this plot, but I hope you can see the difference of really nice spaced out lines with a steep spectrum, narrow spectrum, and really chaotic with a more wide spectrum. Okay, swell generation. Basically, waves come from pressure differentials caused by wind. Wind blows one way, high pressure forms on the backside, low pressure on the front side of the wave. Wind speed is going to increase with your altitude, generally. Also, generally, wind is going to be different speed with, to your left, to your right, forwards, backwards, up, down, and, the time. So we try to use u sub 10 with the vector over it, and that represents wind speed 10 meters above sea level. That's the most common way to represent wind speed leading to swell generation. And as you can imagine, that is very difficult to do, not only in one spot, but over the whole length of an ocean. Lots of approximations are needed. Okay, let's talk about swell generation with respect to direction. So as wind blows downwind, the bumps, the energy, don't just go straight downwind. They're going to form at angles off to the sides of the wind. So this green is going to be our peak frequency, and that's 0 degrees off of the downwind angle. But then as we come to 2 times the peak frequency, we're going to see that at this angle across from the wind, that energy is not just at the center, but it's equally out to here. And then at 3 times the peak frequency, we really have all the energy diagonal of the wind. So there's almost going to be no energy going downwind, but all of it coming off to the sides, which I'm certain many of you have seen in really windy situations, that the wind starts nuking and it's not like you see bumps going downwind, but you see bumps going towards the side. That's this 3 times frequency. And I did not put numbers on here. I did not try to be quantitative with it, but just it kind of gives you an idea. The majority of the energy does go straight downwind at the peak frequency, and then the higher frequency you get, the more it spreads off to the sides. This is really important because it's going to cause a thing called quadruplet wave-wave interaction, and that really redistributes high frequencies to lower frequencies in the spectrum, which we'll cover a little bit later. Okay, this is a complicated slide. We'll do our best. So basically we all know that we need fetch, time, and wind speed for our waves to grow. Of course, gravity being involved with that. But we're going to use this idea of equivalent fetch. So let's pay attention to this diagram I made right here. So you're at the coast, the wind is blowing this way, and here would be the fetch from the coast to this downwind point. Basically, we're going to imagine that there's a wave component moving this direction to this point. So that wave component has a speed of c sub g, and over some time, it's going to travel this distance. This distance would be equivalent to this distance blowing forever. This is called the equivalent fetch right here. So if the wind blew forever here, it would be equivalent to that individual wave component we tracked earlier. Okay, that's nice because we can get rid of our duration. So now instead of depending on time up here, we can get rid of time. As we said before, the equivalence between fetch and duration is made because the wind has had the same time to transfer energy to each individual wave component. At this distance, the statistics for the individual wave component would be equivalent to the wind blowing forever. Because of this equivalence, swell generation can be described by the dimensionless fetch. And this kind of just gives you an idea of how developed a fetch could be. And we see the relationship of fetch to wind speed squared. So if you have a short, so let's say a large fetch and a small wind speed, the ocean is underdeveloped. And if you have a small fetch and a large wind speed, the sea state is going to be very developed. Let's continue a little bit more with swell generation. Fetch limited, there's the definition from the book uses this equivalent fetch, but just plainly speaking, Fetch limited is going to need more distance for the sea state to grow. Duration limited needs more time for the sea state to grow. A fully developed sea is when no more energy can be transferred to the sea. The growth of the sea stops when phase speed of the waves reaches wind speed. Quick little example, storms are winds above 55 miles an hour. They rarely become fully developed due to a lack of fetch. So you would need a 1,118 mile fetch for a wind speed of 67 miles an hour. That's a really big distance and kind of unrealistic. Moving over to this side, the practice of dimensionless parameters may be applied to various statistics, such as significant wave height and dominant period. So in that case, for deep water and a fully developed sea state, dimensionless significant wave height and periods are universal constants. Here we have 0.24 for the wave height and 7.69 for the period. This means that weather conditions are strong storm winds or even a gentle breeze, they would provide the same the same wave height and period values so long as the ratio between fetch and wind speed squared is equivalent. This is another quick one we'll kind of skip by. I really just wanted to show you how researched this is and how over time, there'll be one kind of researcher and then another researcher of, different theories of what's going to make these swells form. So they have different shapes. These are functions. Lots of math. All right, now let's get into the evolution of swell, explained via dispersion and wave-wave interactions. So dispersion, there's going to be directional and frequency. Directional dispersion is the initial energy within the wave field spread laterally. The initial energy within the wave field will spread laterally, therefore spreading the energy over a larger area. Visually, this can be seen as the waves changing from short-crested to long-crested. Frequency dispersion. Since longer waves travel faster than short waves, the low-frequency waves will outrun the higher frequency waves. This is similar to how marathon runners begin at the same starting line, while at the finish, the pack has spread out with the fastest runners arriving first and the slowest arrivers running last. And then we have this idea of quadruplet wave-wave interaction. There'll be an example in the next slide. Steep waves tend to overlap, creating diamond patterns. That transfers energy from higher frequencies to lower frequencies. This process does not remove energy from the spectrum, it only redistributes it. We'll see the example on the next slide. So basically, you have this purple and this red. These are the purple set of waves and the red set of the waves. But where they interact, you get these diamond shapes. These diamond shapes. Same thing over here. Here's the wave number space. I'm describing each wave. And as they overlap, you can look at diamond to diamond as a wave. This has a new wavelength to it. So as you overlap these two, you're going to have two new waves. You're going to have this diamond wave and then this diamond wave here. As they overlap, they're going to resonate and create a new formation of waves as we saw in our linear wave theory. So if the frequency, wave number, and direction of one diamond pattern coincide with those of another diamond pattern, the energy is transferred among the four free components. This creates a resonance that transfers energy from higher frequencies to lower frequencies, therefore changing the shape of the spectrum. And I'm certain y'all have seen this in the ocean where we see these diamonds pop up. So those diamonds are new waves and they are moving faster. The problem is, can you stay on top of those diamonds and keep up with them? Okay, so here's a spectrum evolution example. This is from a buoy off of Topanga near Santa Monica, Los Angeles. And the idea was I tried to find a buoy where there's a long period swell existing, and then some wind starts, and we'll see how the evolution of the spectrum. We'll see the evolution of the spectrum. So I will press play now. Okay, we get a little bit of wind to start. I paused it right there. So here we see in the 3 second-ish period range, we got some bumps starting to form after the wind is picked up. This long period swell is pretty much unaffected. And then as time goes on, it builds a lot. Builds. Even the period starts to build. So we saw the peak earlier at 3, now the period's at 4. And then later at night, after the wind's blown for a while, we really see the focus of energy on this 4 second range. Even a little higher, it's trying to grow. All right, and then now we're back at the beginning. Here was the wind conditions actually. So 19Z to 01Z, we had 20 knots of wind, and then outside of those times, the wind was calm. Next slide. Breaking waves. What is a breaking wave? There's no general accepted precise definition of a breaking wave. So if this is the crest of the wave, where along the crest is a wave break occurring? I think everyone would say here it's occurring. Here probably. Here maybe. Here, who knows? Here, no, it's not breaking. Most would say at least. Over here, similarly, I see many white caps. Is this wave breaking? The point is, we don't really know. Some speculate that wave breaking occurs when the height divided by wavelength equals 0.14. My favorite definition is when a particle moves faster than the speed of the particle above or below, therefore making a wave break. Wave steepness or short crestness exceeds a certain threshold. In deep water breakers, you can call them white caps, popcorn, white horses, jumping rabbits. The Beaufort wind force scale is based to a large extent on the white cap coverage of the ocean surface. And from my own experience, this is not from the book, so just take this as a Matt's observation, rule of thumb. If there's already long period swell in the water, it's going to take more wind to create white caps. So imagine a lake, all of a sudden it's flat, and then all of a sudden you have 20 knots of wind. The lake is going to be filled with white caps in seconds. However, in the ocean, say you have a large 8-second period swell, and then all of a sudden it becomes 20 knots of wind, you're going to have almost no white caps. And where you would see white caps is kind of on the crest of the 8-second period swell as they pass by, because that's where the 8-second swell and the caps would line up to create this particle motion I was talking about, where they move faster than below or above. Another thing about white caps that's just from my personal experience, not from this book, is that white caps are really just reflected light. So there's a lot of times that it's overcast and conditions could be like this photo on the right, but because there's not light to reflect off the white caps, you might not notice all of the caps. So you really got to look at the motion and see how steep the wave is. And then half the time later that day, the sun will come out just 10 minutes later, and you'll see all these white caps appear, but really they were there the whole time. They just didn't have the light to reflect them. Okay, we'll go by this one quickly too. Just kind of showing that there is a lot of math that goes into these wave models. So feel free to research this yourself. And that's it. That's a lot of information there. Like I said, go search this information yourself. The book, again, is called Waves in Oceanic and Coastal Water. There may or may not be a free version online. And let me know what you think. I hope you enjoyed. Keep shredding, I guess.